So, hello everybody, how are you all? I hope you all are fine and safe and doing well in your life and more precisely in your mathematical life, right? So, again, I just came back with another video, and in this video, we are going to tackle a very interesting thing. Like, I have written all the stuffs that we are going to discuss in this video on these two boards. But before looking at that, because I think that's quite messed up, but I will explain you everything. Don't worry. And if I have to just explain it to you with writing itself, that I have a whiteboard with a black marker, I will continue with that itself, right? But before that, just look at me. Like in this video, we are going to use two things. More precisely, two things. That's it. The first thing is, let me just write it down over here. So, using two things, right? Two things. So, first one, like among these two things, the first one is the most famous Euler's identity, and that says that e to the I pi, right, is equal to -1. This is considered as the most beautiful equation in mathematics. It is really is, because we are just, and I don't need to tell you about anything like because this is really famous, and even my WhatsApp DP is just this thing. I have just used this thing as my WhatsApp DP. So yeah, e to the, like, e is a constant, I is the imaginary unit, and pi is a constant. Then when we combine all the three stuffs, like when Euler combined all the three stuffs, then you got to know that it's just -1. And it's not just, it's really unbelievable and really impressive, right? And the second one is, we are going to use the famous Ramanujan paradox that says that all the sum of all natural numbers, that is 1 plus 2 plus 3 plus 4 and dot 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 to infinity, is -1 over 12. Well, it's not proven, because it seems to be, it is just like if we just combine it in summation notation, so it is the series from n equals 1 to infinity of n, and this is the Riemann zeta. Well, this is not the Riemann zeta. This is the Riemann zeta of -1. I hope you know what is Riemann zeta. Riemann zeta of z is the summation from n equals 0 to infinity of 1 upon n to the z, right? And when you just plug z equals -1, you're gonna have this summation, right? Well, when you just plug n equals 0, it's just 0. So it doesn't mean to just write it from 0 to infinity, right? So it is a divergent series, but yeah, Ramanujan has calculated it as -1 over 12. So we are going to use that paradox in our this whole proof or evaluation of something. So I think I should begin with everything right now, because I have explained you what we are going to use in this thing, and now we are good to go. Well, I was wandering on YouTube, and I got to have an integral that was integrating from, like, the integral was something like that. The integral of -1 to the x dx, right? It seems to be easy just using this Euler's identity, but I thought to have an evaluation of this thing when we just replace x with an index variable with that is n, and we are just sending that n from 0 to infinity. So I was about to just saying that, but I was uncurious, like, so I thought to introduce another logarithm, natural logarithm, to just convert this summation into a product, right? So everything seems good. Well, in this video, we are going to just evaluate this summation, right? That's it. Using all these two things. So let's just begin with that. So we have the series from n equals 0 to infinity of ln of -1 to the n, right? So that is equal to, and when you just express this thing in product, so you're going to have that ln times the product from n equals 0 to infinity of negative 1 to the n, right? That's a property of logarithm. And well, I have proved it over here. When you just open this summation, so you're gonna have that ln negative 1 to the naught plus ln negative 1 to the n, as this is going to infinity, right? So this can be written as, when you just have a look at this type of thing, then you're gonna have that ln times all the things are being product to each other. That's what written over here. That's it, right? Well, I'm just looking at this. So this can be written as, there is a property of logarithm, that is, this n is just come outside this whole thing, and this is going to be multiplied with the thing like this thing, right? It's a property of logarithm. And if you're not clear with that, you should just check this out firstly and then come back to this video, right? That's a property. So this is a constant. Well, we're assuming this is a constant. Well, it's not a constant because it's an imaginary thing. Well, it's a constant, I think. Because no, it's not constant again, because we are going to introduce imaginary unit over here. So we are just putting all this stuffs out because it's not related to n, that's why. So ln of negative 1 and times the series from n equals 0 to infinity of n. As I have discussed it right over here, that the summation from n equals 0 to infinity of n, that is the Riemann zeta of negative 1, like Riemann zeta of negative 1, and that was evaluated as negative 1 over 12, and I'm just using that thing. So this thing is just written with negative 1 over 12. So we can see that ln of negative 1, evaluate this from here, taking logarithm both sides, ln e to the I pi equals ln of negative 1. So I pi times ln e, this is 1, ln of negative 1. So ln of negative 1 is being evaluated to I pi, right? So when you just replace ln of negative 1 with I pi, then you're going to have ln of negative 1 that is replaced by I pi. So I pi, negative I pi over 12, right? So far so good. And we have successfully evaluated this series, right? But if we are looking at this thing, obviously if this thing is equal to that thing and this thing is equal to this thing, then this thing is equal to also this thing, right? So I've just written all the things like in such a manner that this thing is equal to this thing, right? This product is equal to this thing that we have evaluated earlier. And I'm just going to take e both side, and all the stuffs are being taken to power. So this thing becomes e to the power of all these stuffs, and on the right hand side e to the power of all these stuffs. Well, if e to the power of ln of something, then something is being taken out as in the bottom, and e to the ln is just vanished. That's another property. So yeah, you should check that out because that's necessary to understand all these stuffs, because where we have already used a lot of properties of logarithm. So yeah, you should just check that out. So the summation, this come out, we are having on the left hand side only the summation, that says that the summation from n equals 0 to infinity of negative 1 to the n. And that's a really cool thing. When you just evaluate that, it's something looks like this. So it's, if we are going to evaluate this thing, that is really creep. So well, and e to the negative pi over 12. So if you just use exponentials properties, it would be just 1 over e to the I pi over 12, right? So far so good. And now our task is to evaluate this thing. That is, this thing we have proved 1 over e to the I pi over 12. And now we are going to use the, well, yeah, another thing I have to use, well, I have mentioned it right over here, looking for Euler's formula that says that e to the power I theta equals cosine theta plus I sine theta, right? And when you just plug theta equals pi over 12, well, it's not 2. Let me just correct it. It's 12. So theta is replacing theta with pi over 12. So if you look closely, then I pi over 12 we are going to have on the left hand side that we need to evaluate, right, for this product. So you just have a look at this. The theta would be replaced with pi over 12. So we are having on the right hand side as cosine of pi over 12 plus I times sine of pi over 12. And pi over 12 is 15 degree, right? So the value of cosine at 15 degrees is this, the square root of 6 plus the square root of 2 over 4, and the value of pi over 12 of 7, sorry, this sine of pi over 12 is I times the square root of 6 minus the square root of 2 over 4. So far so good, right? And actually, more precisely, we're looking for 1 over e to the power I pi over 12, right? So I'm just dividing both sides with 1. So I'm just dividing all the stuffs with each other. That's good, that's good so far. And we are just going to just have this thing on the right hand side, and the denominator is common, so it's gonna be taken out and just sent on to the numerator, and in the denominator we are having this thing only, right? And we know that we don't like imaginary units in denominator, so for the sake of that we have to just multiply with the conjugate of this complex number, and divide with the conjugate of this complex number. So the conjugate of this complex number is the square root of 6 plus the square root of 2 minus I times the square root of 6 minus the square root of 2. Like, I'm looking for the conjugate of this complex number. So we are going to divide and multiply with that. So this thing is multiplied with 4. So it's gonna be in the numerator. Like, keep remember guys, on the left hand side we are having our required expression, that is 1 over e to the power I pi over 12. Keep remember that. And on the right hand side we are having 4 times the square root of 6 plus the square root of 2 minus I times the square root of 6 minus the square root of 2. That's good. And when we just solve this, when you just multiply with these two things, so here we are going to apply a, assume that this thing is a and this thing is b. So a plus b and a minus b, right? Here it is minus. So a plus b times a minus b is a squared minus b squared, right? And when you just solve this, and keep remember that I squared is -1. And when you just put all the things with each other, when you just solve this and put all the or I squared, you're going to have this thing in the denominator. That is the square root of 6 plus the square root of 2 of whole squared plus the square root of 6 minus square root of 2 of whole squared. And when you just solve this to, when you expand this two things, you're going to have 16 in the denominator, and we have factored it out with 4, that was sat on numerator. So we are going to have only 4 in the denominator, and that's it our answer. That is, we have evaluated this thing as this infinite series, and here we are having that the infinite product of n equals 0 to infinity of, let me just share that. The infinite product from n equals 0 to infinity of -1 to the n is being evaluated to the square root of 6 plus the square root of 2 minus I times the square root of 6 minus the square root of 2. That is whole divided with 4. How cool is that? Like, literally, how cool is that, guys? And I don't think that I have messed up somewhere or I did some mistake. I don't think so, because everything is good, everything looks good. I'm just following all the rules that is necessary in this evaluation. So I don't think that I did somewhere any mistake, and if I did, please let me know in the comment section. But so far I did it 2 times and I didn't find any sort of mistake. Again, this looks impossible, and if this is wrong, then because of this Ramanujan's paradox. And if that is wrong, then this is also wrong, obviously. So yeah, I think for today it's enough, guys. I'm not gonna stretch this video so far. So please just attach to me. I will get back to you a lot of things like this. Thank you so much for watching this video, guys.